Hi guys, we're going to continue with equilibrium for weak acids or bases. Now these calculations are going to be very similar to the ones that we used in chapter 7 because as we know, weak acids and bases are like an equilibrium. And the reason for that is because they don't ionize completely, so it's not a complete forward reaction, and for that reason we can use the double-sided arrow. So the math is very similar and the ice tables are very similar to what we saw in chapter 7. So let's just remind ourselves about dissociation of acids. I'm just going to assume you've forgotten everything that you learned yesterday and remind you that the definition of an acid is something that is a proton donor. So in this case, if I have acetic acid dissociating, okay, and it dissociates as an aqueous solution, we can say that it donates its proton to water. And yesterday you learned once we actually add a proton to water, we make this thing called the hydronium ion. Okay, so this is the hydronium ion. And a lot of times, the hydronium ion, it looks like this because we've just added a proton to H2O. But for our purposes, we can also assume the hydronium ion and a proton mean the exact same thing. Okay, so in this situation, we consider our acid as a proton donor. Okay, so it's an acid, and in this case, water will be the proton acceptor. Okay, so since water is the proton acceptor, once it's accepted the proton, we make the hydronium ion, or we're going to call it later on the proton. This will be my conjugate acid. And since my acetic acid gave up its proton, it is linked. And this acetate ion is now the conjugate base because it's got no acid, or I'm sorry, it's got no proton to donate. Okay, so for our purposes of making a Ka equation, and remember I told you a long time ago there was a bunch of Kas, so far, or not Kas, Ks, we've got the equilibrium constant, we've got the solubility constant, now we're going to have Ka, Kb, and Kw that you learned yesterday. Okay, so let's take a boo at this. So when I look at the value for the Ka, we use the equation products over reactants. So we can say my product, my hydronium ion, multiplied by the concentration of the acetate ion, okay, my conjugate base, all over acetic acid. Now, I'm not going to include that water because don't forget, water's liquid. It's a pure liquid. Its concentration does not vary, and for that reason, we don't include it into the Ka equation. This is a lot of the reasons why we don't normally put water in, and we consider our hydronium ion a proton, because if you take water out of the equation, then you can just say you added a proton. Okay, so this is what we would do here. Okay, so in general, you can write it one of two ways. You can have it with the water and you're making the hydronium ion, or you leave water out of the situation because you don't include it in the Ka anyway. So see how in this situation we don't include water. We assume water's there because it's aqueous, and then my hydronium ion is simply H+. Yeah? And this thing works out with pH equations and stuff like that too. Okay, so for our purposes, we can look at Ka in one of two ways. We can look at it from the way I wrote it up here, and this is just a general equation. So I'm using A as my conjugate base, right? So that's with the water included, but we don't actually put it in the equation, or okay, so we can write it one of two ways, and I'll just put that Ka there. Okie doke. And I just realized I left out all my aqueuses, so I'll draw them in just to be consistent. Aqueous. Okay, so these two mean the exact same thing. All right, we're either assuming water's there or we're putting it in the equation but not using it in the Ka formula. Yeah? All right, so let's take a look at another example. So if we look at hydrofluoric acid dissociation, here's my example. So I've got hydrofluoric acid dissolved in the presence of water, and that's what makes it an acid because it's aqueous. All right, and it separates. We could have also said in this situation, just like a regular dissociation, and you would have learned this in grade 11 as well. Okay, so either or, whatever floats your boat. So when you're writing your Ka, you would write and once again, I forgot my aqueuses. Okay, so just assume aqueous, right? And we're not including the liquid water because that's not a thing. Well, it is a thing, but it's a constant concentration, so it doesn't go into this equation. Or we could have written it like this. This is overkill, but that's okay. Okay, so same thing. And when we do pHs, sometimes it's just more straightforward to go straight to the H+, okay, because that's what they're monitoring. But just so you know, hydronium and protons mean the exact same thing for our purposes in an aqueous system. All right, so let's get to the math, shall we? Are you ready? We got a quadratic formula happening now. I know I am. All right, so these are really good test questions. All right, normally there'd be one of these on your final exam. So let's take a look. What is the hydrogen ion concentration? So we're looking for the H+ concentration of a 0.2 molar acetic acid solution. And what you need to remind yourself is that this is a weak acid. So the minute you see weak acid, you think equilibrium, right? So we're going to be dealing with a Ka. So let's set up our ice table, and we'll let X represent the change in concentration, all right? So we're going to set up our ice baby table. Okay, so CH3, COOH, AQ. Okay, so when we take a look at this, they're telling you it's acetic acid. At this stage of the game, you should know what acetic acid looks like and how acetic acid dissociates. So I'm going to do this, and I'm going to go, I personally keep the hydronium atom out of it, or ion out of it, because, I don't know, this is the way I taught it to you in grade 11. I say, why mess with a good thing? But we do show you hydronium because it does come up in life, okay? So we separate my acid into the two ions. Okay, and as long as you see that this is an acid, this hydrogen was dissociated, it became this proton, leaving behind this acetate ion. Okay, so let's do our ice table. So my initial concentration of acetic acid was 0.20 moles per liter. Okay, and initially I have no dissociation, so 0 and 0. Then my change is, because it's a 1-to-1-to-1 ratio, negative X, positive X, positive X. So then my equilibrium concentration, okay, which is what we're looking at Ka, all right, my equilibrium concentration is the change. So 0.2 molar minus X, 0 plus X, and 0 plus X, okay? Now we get to have some fun, all right? So step 2, so step 1 was make my ice table. Step 2, right? Now we've got to sub into our Ka. Okay, so step 1 was this. So Ka should equal my equilibrium concentrations of H+, CH3, COO minus. Okay, all over my concentration of the acid. Okay, so now that we've got that, what do we know? Well, first things first, you need to know what Ka is. And there's a handy dandy reference table, and I'm just looking up the page here. Yep, page 726 in your textbook has the Ka for acetic acid, also known as, and if you remember this from organic chemistry, the UPAC name for acetic acid is ethanoic acid. And when I went and looked it up, it's 1.8 times 10 to the negative 5. Okay, so I had to look that up. So now that we know that piece of information, we can plug it in. Now, sorry about that, guys. So the other important thing is that this actually, that's a different question, but I'm just going to remind you of when we can determine changes are negligible, and this will come up in the next question. But for acids and bases, usually the Kas are even less than, like the threshold for the Ka is even less than 10 to the negative 3. So in this case, we would think that the change is negligible, but that'll come up in the next question, and I'll highlight that later. Okay, so let's plug in our numbers. 1.8 times 10 to the negative 5 equals x times x, because I got them from my ice table, right? See, right here and right here. Okay, all over 0.20, and I'm going to get rid of my concentrations for now. All right. Okay, because it's assumed. All right, I'm going through this step by step. Just sit and enjoy the ride, okay? So, x squared, I've multiplied my two x's. I'm going to bring this up here. So it gives me 1.8 times 10 to the negative 5 multiplied by 0.20 minus x. Oh, I was a little bit high. That's okay. Okay, so let's FOIL this guy out. All right, so so when I FOIL these two out, I end up getting 0.000005 zeros, 36 minus 1.8 times 10 to the negative 5 x. Okay, I just FOILed it out, equals x squared. Guess what? Unavoidable, my people. Quadratic formula. So just to remind ourselves of quadratic formula, I'm going to put it in a nice color. Here we go. So don't forget, quadratic formula. X equals negative b plus minus okay, so looking at this scenario here, when I set it up in the proper terms, 0 equals, and plus, because I brought this guy over, okay, so there's our situation. So we know that A equals 1, B equals 1.8 times 10 to the negative 5, and C equals negative 0.1050. 1, 2, 3, 4, 5, 3, 6. Okay, so now that we've set that up, let's solve for x, shall we? I'm going to give myself a little bit of room here. Okay, so I'm going to go back to purple. Feels like more of a business color here. All right, let's do some business. So x equals negative b plus minus square root b squared minus 4ac all over 2a. So when I sub these numerals inside, so 1.8 times 10 to the negative 5 plus minus Okay. Oh, can't forget that. How many times in my math career did I forget the denominator? That sucks. Okay, so I'm just going to spell it out because that's just the way I do life. So let's square this. This is, when I square 1.8 times 10 to the negative 5, 3.24 times 10 to the negative 10 minus, and when I multiply this by 4, 2 negatives make a positive. Don't mess that up. And I get 0.00000144. Okay? All divided by 2. So then, when I add these two guys together, it's almost negligible because this is 10 to the negative 10. And so the change is pretty much not even visible. So it's going to end up staying here. Okay, did I do the right number of 4 zeros? Yep. Okay, divided by 2. So then, when I take the square root, okay, now let's save ourselves some time. We know, ooh, and I'm almost at the end of this page. Oh boy, I'll figure it out. So we know that we can't have a negative concentration. So because we can't have a negative concentration, we don't even need to subtract these guys. Sorry, got excited there. We are just going to add them. All right, so I'm just going, because there's no point even wasting the space that I don't even really have. So when I add these guys together, I end up getting, so I'm just simply going to add. I'm just going to add, not subtract, okay? So when I add them together, I end up getting 0.003776775, okay? Divided by 2. And my x actually equals 0.00188, and so on and so forth, moles per liter. Now, what the heck does that even mean? Well, that x, I'm just going to swing on up for a moment. That x represents this right here. Okay, so we know that our concentration of hydrogen ion is this value. Okay, so therefore, I'm just going to change in color. So therefore, the concentration of H plus equals X, which equals 0.00188 moles per liter. And how many sig figs do we go to? Ooh, we're only going to 2. So let me fix that. 0.0019 moles per liter. Now there was another little part of the question. Ooh, I can squish it in right here. They're asking me to find the pH. So the pH is the negative log of the concentration of hydrogen ion. Okay, and let's plug that bad boy in. And when I take the negative log of this concentration into my calculatrice, I will get 2.72. So therefore, the pH of this solution is 2.72, which makes sense because it's an acid. If you got something over 7, you screwed up somewhere. Okay? Whew! Hope that worked out for you. Let's try another one, shall we? Okay. Oh, sorry. Forgot about this. If acetic acid were a strong acid, guess what? It's not. But pretend it was, okay? If it was a strong acid, we would assume that it went completely forward. Let's just pretend this, okay? And so therefore, we would assume that everything went forward, Okay, so let me just draw the little ice table for that. So pretend. Okay, so we're pretending, and I'm writing pretend so none of you can say that I told you that acetic acid was strong. So if we said that, we would assume that it was a forward. Notice how I'm only doing one arrow, and it would be H plus aqueous plus the acetate anion. Okay, so we started out, so initial would be 0.20 moles per liter, 0, 0. There is no equilibrium. It would be final. Okay, everything would be gonzo. And we would end up with, actually, hold on. I'm just going to do this. Okay, back to my pen. So the change would be everything, 0.20, because my final, I'm not even going to call it equilibrium, would be 0, right? So if my change there is minus 0.2, then my change here is plus 0.2. Same thing here. So my final would be 0.2 molar, 0.2 molar. Okay, so it's a complete, and the pH for a strong would be negative log of the concentration of H, negative log this. So once I calculatrice that, we're going to end up with a pH of 0.7, which is way stronger. Okay, so no ice table needed. All starting concentration of acid is turned into product. Okay, how's that? Good? All right, one last type of equation or question for weak acids, okay? So let's take a look at this. Don't want to overuse the pink, want to save that for special, so we'll go back to purple. Okay, so a weak acid whose concentration is this has a pH of 4.2. So what this is actually telling me is at equilibrium. Okay, so we can use this. We are going to, step 1, set up our ice table. So it's just a random weak acid. So HA dissociates, and we know it's a weak acid, so we use the equilibrium symbol, okay, into H plus and the conjugate. Okay, base here. All right, so there. We know we're starting out with 0.10 molar. Okay, we know we have no product yet. So my change, it's a 1:1:1 ratio, so negative x, positive x, positive x. So at equilibrium, concentration, okay, good. But we're given this piece of information. So this piece of information can be used to determine our concentration of H plus at equilibrium. Okay, so we can figure out the concentration of H plus at equilibrium by using this formula that you were taught yesterday. Okay, so when I plug this in, you are just going to do 10 to the power negative 4.2. Okay, and on my calculator, I have a little EE button. If you don't know how to figure this out on your calculator, send me a picture of your calculator and I will help you. Okay, so when I plug that in, I end up getting 6.31 times 10 to the negative 5. And since it's a concentration, it's moles per liter. okay? And that's what x is. So okay, we can use that for x. So now that we know what that is, we can figure out something else, okay? So I'm just going to scooch this up. So I know my Ka all right, so now let's plug in our values. We're solving for Ka, so that's the unknown. That's what makes it a different type of question. So I know that normally it would be x times this. Now we've got to figure out now. So once again, this is our very best situation because the math becomes easier. We can assume, you like those sparkles. We can assume because this is so small, we can use our assumption. Too much, guys? We can use our assumption that x is negligible. Okay, we can use our assumption that x is negligible because it's really small. If you do that 100 rule, okay, and it is. So we can just do that on that, which makes life so much easier. All right, back to normal. All right, so if I go back to Ka equals 6.31 times 10 to the negative 5 squared, because I just squared them, 0.10 because I nullified that. And when I do that math, Ka equals 4.0 times 10 to the negative 8. We're going to two significant digits because that was the measured quantity in our question. So there's that. I'm going to stop and do another video for bases. Okay, so feel free to click on right away or take a break. I will give you further instructions, but the homework and the reading are already in the calendar the calendar page once you click on the day. Okay, so I'm going to stop right now, but I will pick right back up. Okay.